Welcome back. I want to finish up ARIO acidity trends. This is part 2. In the previous video, I went over atom electronegativity and atom size. Next was resonance, and I had not done induction yet. This is a way to determine or to order molecules in terms of their acidity. Okay, we are up to I, and just a reminder, part 1, if you want to know what A and R, how to use those trends, that is number 04J20. Okay. This is actually the 4th trend, induction. Because again, A was split up into 2 parts, atom electronegativity and atom size. Sorry. Induction. Yeah, induction. Let me draw a couple of organic molecules. You could pause the video after you see these 4 and copy them, because I want us to order these in from increasing or most acidic to least acidic. Okay, you know the trick. The trick is you're given a set of acids, but determine which one's the most acidic or the least acidic. You want to look at its conjugate base, the CB. And let me draw the conjugate base. Actually, you draw the conjugate base for these 4. Again, we have hydrogens on carbon, but would you rather have the anion on a carbon, or would you rather have the anion on a oxygen? Okay. That would tell you which hydrogen or which proton to abstract or which proton to grab with the base. Go ahead and draw the conjugate bases, pause your video, and I'll be here when you're done. Okay, the conjugate bases are just the oxygen anions, or the, how would I call this? The oxyanions, maybe? Double check my work. All the anions have the negative charge on an oxygen. We can't use differences in electronegativity. We can't use differences in size. None of these anions have resonance, so we can't use the R. We can't use resonance. We are using electronegativity in a different way, though. It's what's called induction, the pulling of electrons through bonds. The pull of electrons through bonds. In effect, we are spreading out the charge, but not via resonance, but via dipoles, or it's called induction. And we have a very electronegative atom here. Maybe not very, but we do have an electronegative atom there. And I know this looks a little strange, but through the bonds, that bromine is creating a dipole towards it. So remember your dipole arrows have that little hash. I know it's curved. Don't worry too much about that. But what that means is that the oxygen is not a full negative 1 charge. It has some electronegative density or electron density pulling away from it. So this is less than -1, technically. But the thing is, the more electronegative atom has a greater pull. Let me write that down. The more electronegative atom has a greater pull. And what that means is it is more stabilizing. It stabilizes the anion more. So it's more stabilizing. So here, actually we don't have anything analogous because I need something on this carbon. And the other choices The halogens are on the first carbon next to the oxygen. But let's compare these two, fluorine and bromine. Which do you think is more stable? The anion that has a fluorine or the anion that has a bromine? See, this fluorine is more electronegative and it's pulling harder than bromine. Okay? But what about these two? They're both bromine. So distance also makes a big difference. And we'll say the closer the electronegative atom is, the more stabilizing, the greater the pull. So the closer the electronegative atom is to what? Closer to the anion, closer to the O minus, the closer the electronegative atom is to the negative charge, the more stabilizing. Okay, I think we have a way to compare these two. We have a way to compare now these two, distance. Do we have a way to compare these two? Yeah, the more electronegative atoms, the more stabilizing. So I hope you would predict that this is more stable than that, the one on the left. Okay, fluorines. It's actually the most electronegative atom in the whole periodic table. And here we have it very close to the anion, the oxygen anion. This is the most stable. If this is the most stable, which one's the most acidic? Is this the most acidic or least acidic? Right? It's an equilibrium, and this is more stable, or the most stable. It wants to lose its proton relative to the other acids. This is number one. This is the most acidic. Okay. Okay. Second most acidic. You have these three. Or really, we should look at the conjugate bases. Out of these three, which one is the most stable? The fluorine. The one with fluorine. This is number two. And then now we're looking at the distance. Well, the bromine closer to the oxygen is more stabilizing than the bromine further away. Number three and number four. Just be careful. You want to label the right molecules. Don't label these when you're trying to label the acidity. These are all bases. Okay, you could label these in terms of stability. Stability, most stable, 1, 2, 3, 4. But if the question is what is the order of acidity, just look at the acids. Okay. Once again, we're looking at the basis, though, to determine the order of the acidities, the order of the molecules in terms of acidity. That's it for induction. Classic case is trifluoroacetic acid. This is called TFA. Am I off screen again? Okay, TFA versus regular acetic acid or just acetic acid. You may ask yourself, aren't we supposed to use resonance here? Because we were told that acetate, when this is an O minus, has resonance. And resonance is important. It comes before induction. But both of them have the same type of resonance, so it's a tie. They both have resonance of the carboxylate when this is O minus. So it's a tie. You have to go to the next trend, which is induction. These fluorines are pulling hard. Okay, you have three of them. This is so much more acidic than acetic acid due to the three fluorines. Okay, and you could play the game. You could put 3 chlorines or 3 bromines, right? You know that fluorine is the most electronegative atom on the periodic table. Okay, I think I have space. Let me do the last one, which is orbital. The last trend. Okay. Number 5. Orbital. And really what you want to be good at is identifying the hybridization. But I agree. you're looking at what orbital is the lone pair in, and I'll give you some rules that determine which one's more stable. But to know what orbitals you have in an atom, you need to know that atom's hybridization. sp, sp2, sp3. Classic example is we have these three acids. Now these are very weak acids. CH3, CH3. See, there's no oxygen, there's no nitrogen. The next one I'll do the one with a triple bond, ethine, ethane, and last one is ethene. Now this is a classic example, but you could also use orbital trends if you're comparing molecules where the proton is on oxygen. You know, oxygen can have also several different hybridizations. Let's not worry about that. Maybe I shouldn't even have brought that up. Conjugate base. This might be a little challenging for some of you. Draw the conjugate bases for each of these. So pretend you have, these are acids, so pretend you have a super strong base to remove one of these protons. Draw me the result. What do the anions look like? Pause your video, and when you're done, unpause it. Okay, how would I draw this? Simply, I would say CH3, CH2. We lost a proton on the carbon on the right, and it becomes negative. It's a carbanion. Over here, oh, maybe I should also draw lone pair, and because we're going to predict where the lone pair is. Okay, this might be a little bit easier to see actually. When that carbon on the right loses its proton, you have a lone pair there jutting out, right? Jutting out. It's linear. Okay, don't worry about geometry right now. Over here, we have the lone pair. I'll put it in the, what is this, the southeast. And we have this. Okay. Here's the trick. Oh. Have I been missing negative charges? Okay, here's the trick. A lone pair in an orbital that's very close to the nucleus is more stable. And if you have a stable lone pair, you have the stable anion. So lone pair closer to nucleus is more stable. And again, we're looking at now the conjugate bases. Oh, this camera's a little overexposed. Do you see that molecule? Okay. How do we know if a lone pair is close to the nucleus or not? Well, this is the trick. S orbitals are closer to the nucleus than p orbitals. On average. Right? Because an s orbital is round, and your electron density is, it's within that sphere. But a p orbital actually has a node right there, right on the nucleus. Okay, and so its electron is on average farther away than the s electron, even if you're in the same period, right? This could be a 2s and this could be a 2p orbital. Okay, you know you have 2p x, y, and z, but I'll only draw one of them. Okay, we're almost there. If the s orbital has an electron closer to the nucleus than the p orbital, then the hybridization that has more s character, that's where the lone pair is most stable. We have sp, sp2, and sp3. So we're looking for s character. Okay. You know that hybridization is when you mix two atomic orbitals to get hybrid orbitals. So if you're mixing an s and a p, that's 50-50. This is 50% s character. You see the math involved? The trick? What about this? the sp2 orbital, or sp2 hybridized carbon, you get those hybrid orbitals by mixing an S, a P, and a P, two P's. So in total, you have 3 atomic orbitals. One out of 3 is S. This is 33%. It's lower S character. And this one is altogether 25%. The lone pair closer to the nucleus is more stable. The lone pair is more stable if it's in an orbital that has a lot of S character. This is the winner. Okay? If your lone pair is in an sp orbital, with all things being equal, that anion is more stable than the lone pair being in an sp2 versus an sp3. You got to know that this carbon is sp hybridized. Now, I know we're supposed to be looking at the conjugate bases, but that's true. When this hydrogen is removed by a base, that lone pair falls into the sp orbital that was part of this bond. Let's take a look at this. This carbon right here is sp2. And yes, when that proton down here is removed by a base, I'm not going to draw the mechanism, but that those 2 electrons fall into the same sp2 orbital that was made, or that is used to make this bond. So ultimately, what are you drawing? You know, you're envisioning these in orbitals. This is an sp2. This is an sorry, that's an sp. Okay. And this one, these are tetrahedral, so sp3. And when you lose one of the protons, that lone pair now is in an sp3 orbital. Which one's more stable? The one with greater S character. Therefore, the alkyne is number 1, the alkene is number 2, and the alkane is number 3. I do have numbers for these. They vary from pKa table to pKa table. They're not very acidic. Okay, none of these are very acidic, but relative to each other, this is the most acidic, and I have this as a pK of 25. Okay, again, it's going to vary, 20 to 30. This one, most people say it's 45. Okay, and the least acidic is the alkane. Okay, no double bonds or triple bonds. pKa 55. Sometimes you'll see 60. This is a very interesting number, a pKa of 55. It is probably the least acidic proton that you will see. If you think back to our first video, the most acidic molecule results in the most stable anion. But this is the least acidic proton that you'll ever see. So this is the least stable anion. And what do we know about these stable anions? It wants to go back. It wants to grab a hydrogen. This is one of the strongest bases that you'll ever encounter because it's the least stable anion. Most basic. Okay? And again, like I said, you're going to see some reactions where you really need a strong base. N-butyl lithium is one of the strongest bases that you'll come across. Looks like that. Okay? Because again, that's very unstable. So it wants to grab a proton to become butane. Last thing for this is that N-butyl lithium can also be drawn with a covalent bond. Okay? N-butyl lithium. Man, I think it should be one word. Strongest base you'll ever see for most of you. That is 5. Atom electronegativity, atom size, resonance, induction, orbital. Okay, but I like to think of it as hybridization. Okay, that is ARIO or ARIO. I was looking this up for the last 3 minutes. I was looking this up online because I wasn't taught ARIO when I was a kid. Um, and I saw some other mnemonics. Before I do that, we actually have one other trend, and that's simply charge. Okay, this is we could call this 6. Okay, REOC if you want, but charge actually is one of the first things you should look at, because if you have H3O plus versus H2O versus OH minus, okay, this is not typically in the mnemonic ARIO because it's so intuitive. Definitely this is the most acidic. It wants to become neutral. And definitely this is the least acidic. Why? Because it doesn't want to be O2 minus. You don't want to add more negative charge, right? You want to make it neutral. So this is very basic. What I would put here is, in terms of acidity, H2O plus is greater than H2O is greater than OH minus. Okay. Again, that should be intuitive that this is the most likely to lose a hydrogen. Let's not use the word hydrogen. Most likely to lose a proton. Okay. You're not really losing a hydrogen because the electrons of that atom stay behind. You're just losing actually the nucleus, which is the proton. Okay. Let me give you an organic example. Let's put some carbons on this molecule. NH3 plus versus NH2 versus NH minus. Okay, it's in the same order. This is the most acidic because it wants to lose its proton to become neutral. This is the least acidic because it does not want to be N2 minus. Okay, again, it does not want to do this. Does not want to lose a proton and become N2 minus. If you want to think about the lone pairs, there are 2 there, and there are 3 here. 5 minus 1, 2, 3, 4, 5, 6. Yep. Okay, so put an X right there. That does not want to happen. Okay, that's charge. So anyway, I'll leave you with this. I like ARIO now that I've seen it, but also online I saw cardio. You can look it up. I forgot. I apologize. I forgot who this is attributed to, but maybe you should look at charge first because that's the most obvious. Okay, that's the most obvious. But then after that, you look at the atom. Okay, atom electronegativity and atom size, resonance. Okay. I think they cheated a little bit. Di is I think dipole induction, and then O is still orbital. Okay. ARIO or cardio, whatever helps you. Again, this trend or the list of trends spans 2 videos, part 1 and part 2. And again, you could use this to determine, I'm not going to do it here, but determine which proton is most likely to be removed. And for instance, if I have this, okay, very complicated. How else can I make this? Oh, let's put a double bond there, and I'll emphasize that maybe you want to consider one of these hydrogens as acidic. What's the most acidic hydrogen? Well, you just have to pick. I don't know why I did that. Let me change this. You could definitely pause the video and recopy this if you want. Okay. Well, you got to pick two sites. Maybe pick this site versus this site, and you have now two sites that become O minus. Well, what trend are you going to use to compare those two to figure out which one's more acidic? Or what trend are you going to use to compare the NH versus the OH? That's how you would do it, right? You would have a pair, figure out who's the winner, and then take that winner, the more acidic, and look at another functional group and see if that's still the winner. Eventually, you'll narrow it down to the most acidic hydrogen without using pKa's. Okay. All right. I'm sure your professor's giving you a lot of practice figuring out which is the most acidic proton, and between two molecules, which molecule is more acidic. And you could use ARIO to do that.